So hi and assalamualaikum. Today our group will present about kinetic concept in nuclear chemistry. So this is our group members. We have Siti Noshariza, Nur Hazrana, Putri Nur Safia and Nur Fatih Najwa.
The study of nuclear kinetics is foundational for a wide range of applications, from energy generation in nuclear reactors to the use of radioisotopes in medicine and industry. Key parameters studied in nuclear kinetics include: the first one is half-life, the time it takes for half of a radioactive isotope to decay. The second one is decay constant, a measure of the probability of a nucleus decaying per unit time. And the last one is reaction cross-section, the probability of a nuclear reaction occurring when a target nucleus is bombarded with particles. Next, we will discuss about Ra's law and reaction order. In nuclear reactions, this concept is applied to radioactive decay and other processes, where the reaction rate is often determined by the properties of the reacting nuclei rather than external factors like temperature or pressure. For most nuclear reactions, the reaction order is first order because the decay rate is directly proportional to the number of radioactive nuclei present. This implies n equal to 1, and the equation is rate equal to Kn. For example, carbon-14 decay, radioactive decay is a first-order process. During this process, a neutron in the carbon nucleus transforms into a proton, emitting an electron and an antineutrino. The decay of 14 carbon is characterized by its half-life of 5730 years, and despite continuous decay, 14 carbon remains in the atmosphere because it is replenished through interaction between cosmic rays and nitrogen-14, and cosmic rays produce neutrons that collide with 14 nitrogen, converting it into 14 carbon.
Nuclear reactions usually take place in a sequence of phases, each of which is referred to as an elementary reaction. Molecularity is the quantity of molecules from the reactant that combine to generate the product. There are three types of molecularity. Next, there are 4 steps in elementary steps in nuclear reactions. Firstly, particle absorption, which the reaction is fast; decay of excited state, which when the reaction is slow; intermediate formation and breakdown, also chain propagation. Next, we can see the example of elementary steps in nuclear reaction. Next, these are the molecularity in nuclear vortex. Additionally, steady state approximation is either the net rate of intermediate formation is equal to 0, or the rate of intermediate formation is equal to the rate at which an intermediate disappears.
I'll start talk about the reaction theory. In nuclear reaction, the particle must collide with enough energy to overcome the Coulomb barrier. This Coulomb barrier is the electrostatic repulsion between the nuclei. So when they have a successful collision, it can lead to fusion, but they have 2 types of fusion, depending on the reacting particle and condition. The first fusion, with a single ice, it requires extremely high energy, which is a temperature, to overcome repulsion and bring nuclei close enough for the strong nuclear force to bind them. On the other hand, the fusion with the double S, it happens when the adsorption of neutron collides with heavy nuclei, that causing it to split into a smaller fragment. Next is the transition state theory. That means an intermediate transition state forms before decay into product. In radioactive decay, an atom releases energy in the form of ionizing radiation. This process continues as the atom transforms into near decay product step by step until it eventually reaches a stable state where it's no longer radioactive. In terms of mechanism, this is common decay, which is alpha, beta, and gamma.
Kinetic studies has impacted areas like nuclear energy, medical isotopes, and radiochemistry. For example, uranium-235 undergo fission when bombarded with neutrons. This process splits the nucleus, releasing stored potential energy in the form of heat and radiation. Once potential energy is released, it is then transformed into kinetic energy, and motion of particles and heat occur, which becomes the driving force behind electricity generation in nuclear power plants. Next, iodine-131 is used where radioactive isotope is taken up by thyroid cells. The thyroid gland will absorb iodine from the bloodstream to produce thyroid hormones. Thus, cancerous thyroid cells will absorb iodine-131. Once it is inside the cancer cells, iodine-131 decays and emits beta radiation that will destroy the cancer cell.
That's all from us. Thank you.